In a remote corner of the Tibetan Plateau, surrounded by some of the tallest mountains and deepest gorges on Earth, China is planning what could become the most powerful hydroelectric project ever attempted. If completed, this single dam could generate enough electricity to power an entire country like the United Kingdom for a full year. But the location China has chosen is one of the most extreme and inaccessible places on the planet. The project would be built deep inside the Yarlung Tsangpo Gorge, a region marked by steep cliffs, violent rivers, frequent landslides, and some of the strongest earthquakes ever recorded. It sits just a few kilometers from the Indian border, on a river that hundreds of millions of people downstream depend on for water, farming, and survival. Supporters say this project could be a major step toward clean energy and help China reduce its dependence on coal. Critics warn it could trigger environmental damage, destabilize a fragile region, and shift the balance of power across South Asia. This is not just an engineering challenge. It is a geological risk, an environmental gamble, and a geopolitical flashpoint. China has built megaprojects before. Over the past 70 years, it has constructed more dams than any other country on Earth, including the Three Gorges Dam, the largest hydroelectric facility ever built. But even by China's standards, this project is different. Some experts believe it would be the most complex and dangerous dam ever attempted, not because of its size, but because of where it would be built and what could go wrong if it fails. In this documentary, we take a deep look at China's plan to harness the power of one of Asia's most important rivers. We'll explore why this dam is being built, how China might construct it, and why earthquakes, landslides, and water politics make this project so controversial. And we'll examine what it could mean for Tibet, for India and Bangladesh downstream, and for the future of water and power in a warming world. China is the largest consumer of electricity in the world, using more power each year than the United States, the European Union, and India combined. And this demand continues to increase as the country expands electric transportation, industrial automation, data centers, and urban infrastructure. For decades, this demand has been met primarily through coal, which still provides roughly half of China's total electricity generation despite large investments in renewable energy. Coal has played a central role in China's economic growth, but it has also made the country the world's largest emitter of carbon dioxide, creating internal pressure from air pollution and external pressure from global climate commitments. As China works toward its stated goal of carbon neutrality later this century, it faces a central challenge: how to replace coal with reliable, large-scale, low-carbon power sources that can operate continuously without depending on weather conditions. Hydropower occupies a unique position in this strategy because it provides steady electricity, supports grid stability, and can be deployed at a scale unmatched by most other renewable technologies. For more than 7 decades, China has pursued hydropower development aggressively, constructing an estimated 80,000 dams of all sizes across the country, more than any other nation on Earth. These include iconic megaprojects such as the Three Gorges Dam on the Yangtze River, which remains the largest hydroelectric power station ever built, with a capacity of 22.5 gigawatts. However, after decades of construction, most of China's major rivers that are economically viable for large dams have already been developed, leaving very few remaining sites capable of supporting projects on an unprecedented scale. Nearly all of those remaining sites are located in the country's far west, particularly on the Tibetan Plateau. The Tibetan Plateau is the highest and largest plateau on Earth, with an average elevation of more than 4,500 meters and a total area roughly 5 times the size of France. Its extreme altitude and cold climate allow it to store vast quantities of frozen water in glaciers, snowfields, and permafrost, which feed many of Asia's most important river systems. Because of this, the plateau is often referred to as the Water Tower of Asia, supplying fresh water to nearly half of the global population through rivers that flow into South Asia, Southeast Asia, and East Asia. Among these rivers are the Indus, the Ganges, the Mekong, the Salween, the Yangtze, the Yellow River, and the Yarlung Tsangpo, which becomes the Brahmaputra once it flows into India. Control over the headwaters of these rivers gives upstream countries significant influence over water availability, flood timing, sediment transport, and long-term agricultural productivity downstream. From Beijing's perspective, the Tibetan Plateau is not only a vital ecological region, but also a strategic asset tied to energy security, water security, economic development, and territorial control. It is within this context that China's plan to build a massive hydropower project on the Yarlung Tsangpo River must be understood. The Yarlung Tsangpo begins at the Angsi Glacier in western Tibet and flows eastward more than 1,000 kilometers across the plateau before reaching the eastern Himalayas, where it makes an abrupt turn around Namche Bawa, a mountain rising more than 7,700 meters above sea level. This dramatic curve, known as the Great Bend, marks the entrance to the Yarlung Tsangpo Gorge, the deepest river gorge on Earth when measured from riverbed to surrounding mountain peaks. Over a distance of less than 100 kilometers, the river descends from elevations above 3,000 meters to below 600 meters, creating one of the steepest natural drops of any major river on the planet. This combination of high water volume and extreme vertical descent gives the Yarlung Tsangpo extraordinary hydropower potential, far greater than that of most rivers already dammed in China or elsewhere. After leaving Tibet, the river flows south into India's Arunachal Pradesh and Assam regions, where it is known as the Siang, and later the Brahmaputra, before continuing into Bangladesh and eventually emptying into the Bay of Bengal through one of the world's largest river deltas. The Brahmaputra basin supports hundreds of millions of people who depend on its seasonal floods to replenish soil nutrients, sustain agriculture, and maintain fisheries. Any major alteration to the river's flow therefore carries consequences that extend far beyond China's borders. Historically, the Yarlung Tsangpo Gorge remained one of the most isolated and least understood regions in Asia. Its extreme terrain, dense forests, frequent landslides, and political isolation made it inaccessible even to colonial surveyors during the British period in India. And the river's exact course through the eastern Himalayas was not fully mapped until the 20th century. Even today, the gorge remains sparsely populated and poorly connected to the rest of China, with reliable year-round road access established only in the early 21st century. This remoteness has helped preserve an extraordinary level of biodiversity. Scientists continue to document new plant and animal species in the region, including mammals identified through camera traps, highlighting how little human disturbance the area has experienced compared to more accessible river valleys. From an engineering perspective, however, the same characteristics that make the gorge remote and dangerous also make it uniquely attractive for hydropower development. Hydroelectric energy depends primarily on water flow and height difference, known as hydraulic head. The Yarlung Tsangpo at the Great Bend offers both in exceptional measure. Rather than relying on a massive concrete wall to create artificial height, engineers can theoretically exploit the natural drop already present in the landscape. This has led Chinese planners to consider designs that differ fundamentally from traditional storage dams. Instead of constructing a single massive barrier that blocks the river and creates a large reservoir, the most widely discussed concept involves a run-of-the-river system combined with long diversion tunnels. In this design, water would be diverted from the river upstream of the Great Bend and channeled through a tunnel bored directly through the Namche Bawa Massif, emerging far downstream at a much lower elevation. As the water passes through turbines housed in underground power stations, it would generate electricity before being returned to the river. Because the energy is derived primarily from the vertical drop rather than stored water volume, such a system could potentially generate enormous amounts of electricity while creating a smaller surface footprint than a conventional reservoir-based dam. Some estimates suggest that a project of this type could reach a capacity of as much as 60 gigawatts and generate up to 300 billion kilowatt-hours of electricity per year, nearly 3 times the annual output of the Three Gorges Dam. If realized, this would make it the most powerful hydropower installation ever constructed. Despite these advantages, building such a project in the Yarlung Tsangpo Gorge presents challenges that go far beyond those faced by previous Chinese megaprojects. One of the most immediate obstacles is access. Transporting heavy machinery, construction materials, and a workforce numbering in the tens of thousands into a narrow, mountainous gorge would require extensive infrastructure development before construction could even begin. Tunnels potentially 40 to 50 kilometers in length would need to be excavated through hard, unstable rock under extreme geological stress. For comparison, the Channel Tunnel between the United Kingdom and France is roughly 50 kilometers long and took 6 years to complete under relatively stable geological conditions. In the eastern Himalayas, tunneling would occur in a region shaped by ongoing tectonic collision between the Indian and Eurasian plates, where rock formations are heavily fractured and prone to sudden movement. This tectonic activity is not hypothetical. The Yarlung Tsangpo Gorge lies near the Indo-Tsangpo Suture Zone, The boundary formed when the Indian subcontinent collided with Asia approximately 50 million years ago. This collision continues today, generating frequent earthquakes throughout the region. In 1950, the area experienced one of the most powerful earthquakes ever recorded on land, with an estimated magnitude of 8.6. The quake triggered massive landslides that blocked the Yarlung Tsangpo and its tributaries, forming temporary natural dams. When these dams failed, they released destructive floods downstream, killing hundreds of people in what is now India's Assam region. Similar seismic events have occurred repeatedly throughout the 20th and 21st centuries, demonstrating that major earthquakes in the region are inevitable rather than exceptional. Any hydropower project here would therefore need to withstand not only ground shaking but also secondary hazards such as landslides, rockfalls, and sudden changes in river flow caused by upstream blockages. Landslides represent an additional hazard even in the absence of earthquakes. The steep slopes of the gorge, combined with heavy monsoon rainfall and glacier melt, make slope failure common. In recent decades, several large landslides have temporarily dammed sections of the Yarlung Tsangpo, causing water to back up behind debris barriers that later collapsed. In early 2021, a massive ice and rock avalanche originating from a melting glacier blocked part of the river upstream of the Great Bend, an event visible in satellite imagery, although this particular blockage did not result in catastrophic downstream flooding. It demonstrated the vulnerability of the river system to sudden natural disruptions. Climate change is likely to increase these risks over time by accelerating glacier retreat, destabilizing permafrost, and altering precipitation patterns, potentially increasing both the frequency and magnitude of landslides and glacial lake outburst floods. For a hydropower system that depends on precise control of water flow through tunnels and turbines, such unpredictability presents serious operational and safety challenges. Beyond geology and climate, the ecological implications of the project are significant. The Yarlung Tsangpo Gorge is recognized as a global biodiversity hotspot, containing a wide range of ecosystems from alpine grasslands to subtropical forests within a relatively short vertical distance. Many species in the region are endemic, meaning they exist nowhere else on Earth. Altering river flow, even without creating a large reservoir, can disrupt aquatic ecosystems by changing water temperature, sediment transport, and seasonal flow patterns. Sediment transport is particularly important for downstream regions. Rivers like the Brahmaputra carry vast amounts of sediment eroded from the Himalayas, which is deposited across floodplains and deltas during seasonal floods. This sediment replenishes soil nutrients, supports agriculture, and helps maintain delta elevation in the face of sea level rise. Large dams typically trap sediment behind their structures, reducing the amount that reaches downstream areas. Even run-of-the-river systems can affect sediment movement depending on their design and operation. Reduced sediment flow could have long-term consequences for agricultural productivity in India and Bangladesh, as well as increased vulnerability to erosion and flooding in the Brahmaputra Delta. These concerns are central to objections raised by downstream countries, particularly India, which has repeatedly expressed concern over China's upstream dam-building activities. India and China share a long and contested border, with unresolved territorial disputes and a history of military standoffs, including a deadly clash in 2020 that resulted in casualties on both sides. Water security is increasingly viewed as a strategic issue in this context. Although China has stated that its hydropower projects are intended solely for domestic energy generation and will not significantly reduce downstream flows, the lack of transparent data sharing fuels suspicion. Seasonal manipulation of water flow, even without permanent diversion, could potentially exacerbate floods during the monsoon or reduce water availability during dry periods, giving upstream countries leverage over downstream neighbors. While there is no public evidence that China intends to use water as a political weapon, the possibility alone shapes regional policy responses. In response, India has announced plans to develop its own hydropower projects on the lower reaches of the Brahmaputra, including a large dam in Arunachal Pradesh intended to improve flood control and water storage. While such projects could enhance India's water management capacity, they also increase pressure on the river system and raise concerns in Bangladesh, which lies downstream and has limited influence over upstream decisions. For China, development of hydropower on the Yarlung Tsangpo aligns with several broader objectives beyond electricity generation. It supports economic development in Tibet and other Western regions, strengthens infrastructure and state presence in border areas, and demonstrates technological capability on a global stage. Chinese state-owned engineering firms have extensive experience constructing dams domestically and internationally, including projects in Africa, Southeast Asia, and South America. However, few of those projects match the geological complexity of the eastern Himalayas. Official Chinese planning documents, including references in national 5-year plans, indicate that development of the lower reaches of the Yarlung Tsangpo is considered a strategic priority. Public statements by executives of major state-owned power companies have suggested that feasibility studies and preparatory work are underway, even if final designs have not been publicly disclosed. The lack of detailed information has fueled speculation about the project's exact configuration, timeline, and cost, which could reach tens or even hundreds of billions of dollars. What is clear is that any attempt to harness the full hydropower potential of Yarlung Tsangpo Gorge would push current engineering capabilities to their limits. It would require advances in tunneling technology, seismic-resistant design, real-time monitoring, and emergency response planning on an unprecedented scale. Success would mark a major milestone in large-scale renewable energy development. Failure could have consequences extending across borders and generations. As China weighs these risks against potential benefits, the Yarlung Tsangpo Super Dam stands as one of the most ambitious and controversial infrastructure projects ever proposed. As discussion around the Yarlung Tsangpo project continues, one of the most important questions remains how China would actually build and operate such a system safely over the long term. While official designs have not been released publicly, engineers and researchers studying the project generally agree that a conventional reservoir-style dam would be extremely risky in this environment. A massive surface dam holding back a large volume of water in a deep, unstable gorge prone to earthquakes and landslides would create unacceptable danger for downstream communities. As a result, the most realistic approach appears to be a run-of-the-river system designed to minimize water storage while maximizing energy extraction from the natural elevation drop. In this configuration, the dam's structure itself would be relatively modest, serving primarily to divert water into underground tunnels rather than to create a large reservoir. The main engineering challenge would lie not in the height of the dam wall, but in the excavation of long, high-capacity tunnels through solid mountain rock. These tunnels would need to carry enormous volumes of water, potentially exceeding 2,000 cubic meters per second, while maintaining structural integrity under extreme pressure and seismic stress. Inside the mountain, a series of underground powerhouses would house multiple turbines arranged in cascade, allowing the same water to generate electricity several times as it descends toward the downstream outlet. This approach would allow engineers to exploit the full vertical drop of the Great Bend, while reducing the amount of water impounded at any one point. However, the complexity of such a system introduces its own risks. Long tunnels increase exposure to rock bursts, tunnel collapses, and water ingress under high pressure. Managing heat, ventilation, and worker safety deep underground would require advanced systems and continuous monitoring. Construction timelines could extend over decades, with costs escalating as geological surprises are encountered. The scale of excavation alone would rival or exceed that of any tunneling project ever attempted. In addition to physical construction challenges, operating a hydropower system in such an environment would require sophisticated real-time monitoring of seismic activity, river flow, sediment load, and structural health. Sensors embedded throughout the tunnels, turbines, and surrounding rock would need to detect early signs of stress or instability. Automated shutdown systems would be required to rapidly reduce water flow in the event of an earthquake or upstream blockage, minimizing the risk of damage or uncontrolled release. Emergency response planning would need to account for scenarios in which access roads are cut off by landslides or extreme weather, potentially isolating facilities for extended periods. These requirements significantly increase both the technical complexity and long-term operating costs of the project. Beyond engineering considerations, the Yarlung Tsangpo Super Dam raises profound environmental questions. While a run-of-the-river design may reduce surface flooding compared to a large reservoir, it would still alter the river's natural flow regime. Seasonal variations in water flow play a critical role in maintaining downstream ecosystems and agricultural cycles. The timing, duration, and intensity of monsoon floods influence soil fertility, fish migration, and wetland health throughout the Brahmaputra basin. Even small changes in flow patterns can have cumulative effects over time. One of the most significant concerns relates to sediment transport. The Brahmaputra is one of the most sediment-rich rivers in the world, carrying vast quantities of silt eroded from the Himalayas downstream each year. This sediment is essential for maintaining the productivity of floodplain agriculture in Assam and for sustaining the massive delta in Bangladesh, which is already under threat from sea level rise and subsidence. Any reduction in sediment delivery could accelerate coastal erosion and increase the vulnerability of low-lying areas to flooding and storm surges. While engineers can design sediment bypass systems to allow some sediment to pass through hydropower facilities, no system is perfectly efficient, particularly at the scale envisioned for the Yarlung Tsangpo project. The ecological impacts would not be limited to sediment alone. Changes in water temperature caused by diversion through underground tunnels could affect aquatic species adapted to specific thermal conditions. Reduced flow in certain river sections could impact habitats for fish, invertebrates, and riparian vegetation. The gorge's unique biodiversity, including species found nowhere else, makes these impacts especially concerning. Environmental assessments conducted in other parts of the world suggest that even projects designed to minimize surface disturbance can have far-reaching ecological effects over time. Cultural impacts must also be considered. The Yarlung Tsangpo Gorge holds deep spiritual significance for Tibetan communities, who view the river and surrounding landscape as sacred. Local traditions, religious practices, and historical identity are closely tied to the river's natural state. While the region is sparsely populated, development on this scale would inevitably bring an influx of workers, infrastructure, and state presence, altering social dynamics and land use patterns. Resettlement, even if limited, could disrupt traditional livelihoods and cultural continuity. Such concerns are rarely central in state-led infrastructure planning but remain important for understanding the full human cost of the project. Internationally, the proposed dam continues to influence relations between China and its downstream neighbors. India, in particular, views the project through the lens of strategic vulnerability. The Brahmaputra is a lifeline for northeastern India, supporting agriculture, hydropower, transportation, and ecosystems. Any upstream intervention that affects water flow or sediment supply is therefore seen as a potential threat. Although China has occasionally shared limited hydrological data with India, particularly during the monsoon season, there is no comprehensive binding agreement governing water use on the Brahmaputra. This lack of institutionalized cooperation contrasts with river basins in other parts of the world, where treaties and joint commissions provide mechanisms for dispute resolution and data sharing. Bangladesh, as the most downstream country, has even less leverage. Its deltaic landscape depends on consistent sediment delivery and seasonal flooding to counteract sea level rise. Changes upstream could exacerbate challenges already posed by climate change, population density, and limited land availability. The prospect of multiple large dams along the river, including those planned by India, raises the risk of cumulative impacts that no single country fully controls. These dynamics highlight a broader issue facing transboundary rivers globally. As climate change intensifies water scarcity and variability, competition over shared water resources is likely to increase. Infrastructure projects that might once have been viewed primarily through a domestic development lens now carry regional and global implications. China's approach to the Yarlung Tsangpo reflects its broader development philosophy, which emphasizes large-scale technological solutions to resource constraints. This approach has delivered impressive results in many areas, including renewable energy deployment, transportation infrastructure, and poverty reduction. At the same time, it has sometimes underestimated environmental and social costs, leading to long-term challenges that are difficult to reverse. The Three Gorges Dam, often cited as a precedent, illustrates both the potential and the pitfalls of megaprojects. While it has generated enormous amounts of electricity and improved flood control on the Yangtze River, it has also been linked to landslides, ecological degradation, and the displacement of more than 1 million people. Lessons from that experience inform current debates about the Yarlung Tsangpo. But the unique geological and geopolitical context means that past solutions cannot simply be scaled up without adaptation. From a global perspective, the project raises questions about the future role of large hydropower in a decarbonizing world. As countries seek to reduce emissions, interest in renewable energy is growing rapidly. Solar and wind power have expanded at unprecedented rates, but their intermittency creates challenges for grid stability. Hydropower, particularly large-scale projects, offers a way to provide reliable baseload power and support energy storage through pumped systems. However, the environmental and social costs of large dams have led many countries to reconsider their viability in this sense. The Yarlung Tsangpo project represents a test case for whether it is possible to develop hydropower at an extreme scale while adequately managing risk, protecting ecosystems, and respecting downstream interests. The outcome will likely influence energy planning far beyond China. As of now, there is no publicly announced construction start date for the Yarlung Tsangpo Super Dam. Preparatory work, including geological surveys, infrastructure development, and feasibility studies, appears to be ongoing. The sheer complexity of the project means that even if political approval is firmly in place, actual construction could take many years or even decades to complete. During that time, conditions may change. Climate impacts may intensify, technological alternatives may become more competitive, and regional political dynamics may evolve. These uncertainties add another layer of risk to an already ambitious undertaking. Ultimately, the decision to proceed reflects a calculation that the benefits of harnessing the river's immense energy potential outweigh the risks involved. For China, success would mean a major expansion of clean energy capacity, reduced reliance on coal, and a demonstration of technological leadership. Failure, by contrast, could result in environmental damage, international tension, and long-term instability in a region already under stress from climate change and geopolitical rivalry. The Yarlung Tsangpo Super Dam therefore stands not only as an engineering challenge, but as a symbol of the broader choices facing humanity in the 21st century. How to meet growing energy demands while managing environmental limits and shared resources in an interconnected world. Whether this project becomes a landmark achievement or a cautionary tale will depend on decisions made long before the first turbine ever begins to turn.